tests are mandatory. There are some rules set by the institute and all. So what we will do the next week, probably next Friday or next to next Monday, I will let you know the exact date. So there we will plan one Viva. Okay, 1-to-1 Viva. And after that, we will go for one online class test within something. Okay, so next week, there will be 1-to-1 discussion, 1-to-1 Viva. Okay, so next that the date will be mostly, let me check. Maybe it will be in the extra slot, Friday, or maybe next Monday, 28th, so that we can schedule the class on Friday, 25th. So I will let you know the final dates. So just try to be prepared. So far, we will try to finish the modeling part, and then some part of design we will start next week. Okay, so let's start now. Maybe most of you have joined already. Can you share my screen? So last year, yesterday, we were discussing about Petfinet. We just discussed about the basic formal definition of it, and for rest of our discussion on Petfinet, we'll follow this slide by Dr. Chris Lang. Why? Because these slides, these contents are well developed, and the contents are taken from a few recent research, not very recent, a few, few research papers and few detailed discussions on Petfinet. Now, this is just some history that the Petfinet was first proposed by Carl Adam Petfi on 1962. But at that time, whatever Petfinet we are considering today in our embedded design, those all the features like handling the timing scenario or object-oriented concepts, those are not there in their, those were not there in that, initial version of Petfinet. But this Petfinet is very much useful when we consider concurrency or synchronization, I should say concurrency and synchronization in our distributed scenario. We will check with some examples step by step. Let's say this is a simple example of by the way, my slides are visible, right, today?
Yes, small one. They're like.
It's a small, okay. Now it's fine? Full screen?
Yes, ma'am.
Okay. So this is one example of electronic fund transfer system. When we do online transfer or when we input our pins, this is one simulation of, this is one typical modeling of that scenario. What we are doing here, see, here we are considering 4 digits. Okay, D1, D2, D3, and D4. And in each step, we are entering these D1, D2, D3, D4, etc. But step by step, how we are going to consider the steps of it. Initially, we are entering 1 digit, and at that point, if we press OK, of course, our pin will not be accepted because that is our wrong pin. Then one by one, if 1, 2, 3, this way we are entering our related digits, and after entering the 4th digit, we should press OK or submit, whatever buttons you have. Maybe in some cases you have OK button, enter button, whatever you have, that is pressed. Then there will be some, backend module that will check whether your pin is correct or not. So Based on that, it will give some approved or reject input. And based on that, your request will be either approved or rejected. So that this is the example of basic state transition diagram, when we are talking about this type of electronic fund transfer or doing any transfer based on your entering or PIN. So what will be the equivalent pet design modeling of this scenario? See, in this case, this is the initial state. When we are considering the places and the token, this is basically our states, and these parts we are considering the events. We are entering one events, one digits, and those are creating events. So the basic idea is these state or these token is going through some state transitions based on the events entered in our system. So initially it was first the token is the initial point, initial place. Then you have entered one digit. Okay. This is not. You have entered one by one digits. If first digit, your token will come here at this point. Then if you are pressing OK, this event is getting generated and it is going to the rejected state. Similarly, if the OK is not pressed, then you are proceeding in this direction. You are pressing one digit, token is coming here. You are pressing the token is coming at D2. Then again you are entering another digit, token is coming at D3, and so on. So this is how you are actually translating your previous state transition diagram to this PetFinet language in terms of some states, in terms of some events, and in terms of some transitions or flow relations. So there may be two scenarios in this case. One is normal, you can understand, and one is exceptional. Whether you are entering three or lesser digits, that condition can be considered exceptional. And at that stage, of course, your token, you can see the movement of this token. It is moving to approved state, otherwise it may moving to rejected state. So I may skip this. You can see by yourself the movement of tokens. I think by now you have got the idea. So this typical theory part we have already discussed what we mean by places, transitions, and arrows based on our yesterday's discussion. I'm not going to this part. This is another example, more practical example related to our vending machine. So when we model a vending machine, what we have to consider in our specification. If you want to take a Coke or a snack packet, anything, you have to enter some typical coins. And in some cases, you may get the return in terms of exchange. In some cases, that is not possible. So these type of vending machines, when you are modeling, these may be your state transition diagram. That means initially you are entering, you have not entered any money. So there is 0 cent state. Then you are depositing one by one, maybe some your 5 rupee coin in terms of Indian scenario, of course, 5 rupee coin, then maybe some 10 rupee coin, and then you are moving to 50 cents. At this point, you may take a 50 rupee or 50 cents snack, or if you are interested to take maybe 20 rupee snack, 20 rupee Coke or something like that, then you have to deposit some more cents, some more money. That means some added extra 5 cents, and then only you can move to this 20 cents path and you can take this 20 cents snacks from the snacks bar or from the vending machine. So when we are considering these type of state transitions, this is the example how we are considering the states, how we are considering the events, and we are considering the movement of our tokens. So here also you have to consider all the different scenarios, what are possible coin options you have, what are the total, what can be the different options you have in the vending machine, and what are the maximum or minimum cost of them. And you may have different 5 rupee options, you may have 10 rupee options, may have 20 rupees options. So you have to, so based on that, you have to consider all your additive relations, and that you should, based on that, you actually, based on all possible events, you actually consider your different paths in your Petfinet. For example, since here you have only considered that this vending machine, whoever is using, they are having only 5 cents or 10 cents options. So based on that, we have to consider how we can actually form 5 cents, 15 cents or 20 cents to access all the options present in the snack bar, right? So you can again see those movements, and that way you can understand how the states are changing based on your deposits. So I'm just skipping this part to go through these examples. Okay. Then there is another option, another similar example about a restaurant. You can check that by your own. I will upload this slide where I will come to this part and discuss here. So when we are considering net structures or Petfinets, we are typically interested in this type of modeling because it supports both synchronization and concurrency in a smart way. So this is the concurrent execution you can see that when you are having, you can go a bit back. So from this initial place, from this initial point, the tokens are can go in some concurrent paths based on the event you have described, based on the condition you have described in this point E1. Okay. So these are there can be non-deterministic events, how to model them. These parts can be cleared when we are considering this Petfinets. Now, these are very disturbing actually. So basically, what we are interested in, Petfinet is in this way supporting two main things. One is synchronization. That means we are considering different tokens at the inputs, and they should be considered together when we are considering the effect of this E1. So synchronization modeling is easier in case using Petfinet. Another one is this is one example how we are considering both synchronization and concurrency. Okay. So in this case, we are considering the synchronization, and after event E1 has been applied, the tokens are taking according to your set specification space rule. It may take some concurrent paths. Now we will come to a practical example where we can see that both concurrency and specifically synchronization, both I should say this is more about concurrency. Both producer and consumer both are working together in some concurrent paths. So here you see this is a producer consumer example. Producer consumer example in practical scenario, what you can think? Can you give me one example where you need to model this type of producer-consumer scenario? Anyone? Hello? In your system, whatever you use. Some producer-consumer scenario in your embedded system scenario, or what you generally use in your everyday usage. Anybody? No? Can you think about the printers? How they work? So if you think that you have instructed your printer to print some document, okay, so your main system is basically, maybe you're generating some document, one single document or multiple documents, and you are sending that to your print queue. So at that time, that your main system, this one is a producer, okay, and your printer from the print queue is actually consuming some inputs and instructions, and then it is performing the printing job. Now you understand that while you are modeling this producer-consumer scenario, it is not necessary that your producer, sorry, I will go back to this slide first. Yes, that your producer and your consumer will be working always in the same speed. This is not always possible. That's why you have to consider, whenever you are considering these type of modeling or thinking about designing this type of producer consumer system, you have to think about some storage, intermediate storage. What is the purpose of the storage? When there's a difference between the rate of processing from producer's part and consumer's part, these storage will act as an intermediate buffer. Maybe. So maybe your producer is producing 5 documents and your printer is your system is sending 5 documents. There is a intermediate buffer who is holding those inputs, and consumer at its own speed, printer at its own speed is considering and taking those as the inputs, and it is performing the printing process. Okay, so this is one practical example where we should think about this producer consumer system. There are many, if you check and think different scenarios, you will find different examples. So when we are actually modeling this, we can see how we can actually model that with this Pfeffinath modeling technique. Here we have seen that we have decided the states for our producers and consumers.
Ma'am, but
yes.
Isn't it like usually same for everything? Like even if we go for automobile manufacturing, there's a producer and then there's storage.
Yes, always, anything, anywhere you can think. That's why there are many examples. I have just given one example. Producer, consumer, and this is a typical, this is an example system. That is, there are huge applications of this scenario. That's why we are interested to know how we can model these type of typical scenarios.
And ma'am, what is this like k is equals to 1, k is equals to 5 here?
I will come into that. I will come into that. So now you know producer and consumer. Producer is producing some output and it is sending the consumer to consume. Okay. So that means there are some different states of producer that we have defined: idle, produce, ready, and send. Okay. So idle means when producer is doing nothing. Then this is, you can see this is these are the states, and this is the produce. You can see this is one event. Okay. So when a producer is idle, from there it is if some produce event is giving input or is occurring due to the produce event, this state transition is taking place from idle to ready. Okay. Now, this is the, for these states, This may be it may be anything. This may be the token, I mean boundedness of the state. Boundedness means if it is the state, we can say k bound. That means maximum k tokens can be possible in this state. Here, this is k is equal to 1. This may be anything. Okay. Then one by one, this is send another. This is another event. Produce is one event and send is another event. When send with this event send, this whatever there in your ready state, this token is moving to storage. Okay. Now here you can see this is k is equal to 5. That means storage plus this P3 can hold maximum 5 tokens at a time. Okay, that is its k boundedness. Then I'm coming to this consumer part. You are having these states ready and accepted. And when you are applying this accept event on this ready, you are moving to ready to accepted state. Okay. And then it is consuming. Consuming means it is doing whatever it wanted to do with that instruction or that input. And then once that consume event is done, it is again becoming ready to accept another input. So this is the how you can think the state transition of your producer consumer scenario. Okay, this is a state transition state transition diagram. And I mean that is realized by PetVNet states and events. So again you can see based on this see k is equal to 2. That's why it is k bounded. That means 2 bounded. That means 2 tokens are possible. Okay. So again you just so the token will move and you can see how these tokens are passing. So this is like producer is in idle state to ready state when it is moving. Then with the same event it's sending this token to storage. Then again consumer is accepted by this accept event accepting, and this ready it is going to accepted state and consuming, and this is going. So this is one example. Now what we are interested in, I'm just minimizing this. There are different states. You can check by your own. You can go step by step with the slides, and you can see how with different events, in different events, these states of the tokens are changing. Yes. But what we are interested in, this way we know how we can actually design, how we can realize one PetVNet from a state transition diagram. We have our specification. We know how to design the state transition diagram from it, and from the state transition diagram, with its typical, we can come to this typical representation of PetVNet. Now, what is the important part of PetVNet? With this design, what we can do, we can actually analyze our model based on some behavioral properties. Okay. What are those properties? One is reachability. Reachability, wait, yeah. Reachability means what? Can we reach one particular state from another? That means if you think that my token at some point will be placed, my token or tokens will be placed, maybe I have 2 or 3 tokens that will be placed in some P3, P5, P7 or whatever states I have. The reachability tells that is this combination possible. Next one is boundedness. Boundedness means will a storage space overflow? That means again we have told that, remember whenever we have talked about place type of nets also yesterday, we define some maximum limit, maximum capacity of one place, that maximum numbers of tokens you can place in that set. So that defines the boundedness. So PetVNet bounded means that there is no storage overflow. That means whatever tokens any place can hold maximum number of tokens. Everything is within the limit. And the third one is liveness. Liveness means will the system die in a particular state? What does it mean? Means maybe with your different transitions, considering your all possible scenarios. You have seen, right? Whatever examples we have taken, we have not only considered the states, we have not only considered the transitions and the events, we have also considered different scenarios for different examples. Rather, we have to consider all possible scenarios, whatever we can think of. And we have to check whenever, based on those scenarios, I am reaching to some particular test, a particular state, if my token is getting stuck there, or there is some way that my token, my state, there is another next possibility of some state transition. So if there is there is no more further transition is possible, then we will consider the system is done. Okay. So again, take one example. So you can check this vending machine, or these typical previous examples. These reachability, boundlessness, those are maintained. I will come to one example where you will see there is a failure of this properties. So that will be interesting. So this is the you can come here. So we are checking this vending machine. In this vending machine, again, when we have to check whether the reachability means what? How can we check that? We will do that based on some marking state. Okay. So marking is a state. What does it mean? That means whenever your token is moving at a particular place, you are checking what is the marking. Marking means at present, if you are considering, see first, how many number of states are present here? P1, P2, P3, P4 and P5, right? So that way, in your marking matrix, you will have 5 different columns. Number of states will give you the idea of number of columns. So this is giving the values of P1, P2, P1, P2 and so on, P5. Okay. So whenever your token is, you can see, I can go back a bit. You can see if your token is in P1, that means this is your marking state 1 and all 0. That means the token is present in P1 and all other states are having value 0. Number of tokens 0. Again, you are moving to P2 and you are defining M1 when the token is in state 1 and all is 0 and so on. You can check this P3, P4 and P5. The same concept. This way, when you are defining all the transitions, you can see what are the possible M0 to M4 values are. That way, when you are taking any arbitrary composition, let's say now I will check some M unknown. That is maybe 0, 1, 1, 1, 0. Anything. And with different transitions possible, I will check whether these transition is at all possible or not. Okay. So for that, this is my initial marking M0. From there, what I can see, I will consider all the possible transitions. See, M0 to, if I make a transition T1, I'm coming to M1, M1 to M2, and so on. This way, I'm M3, again I'm coming back to M3, M0, M4. I will continue this until I'm getting some repetitions. Okay. So this way, these are the states I'm checking how they are reachable. And this is giving this reachability analysis. Actually, this is not done alone. We will see how this gives us some idea about our boundedness and how it is related to some deadlock detection or liveliness detection also. So that means we are checking that for any firing consequences, I'm checking if M2 or anything is reachable from M1 and M4 or not. So this way, different scenarios possible, and you can choose different marking entries, and you will check whether those type of states are at all reachable or not according to your modeling or in your design. Okay. Next is boundedness that we have already talked about. A Petminess is said to be k-bounded or simply bounded if the number of tokens in each place does not exceed a finite number k. So k is the bound of that place. Next is the liveliness. This is the formal definition of it. The Petfinet with initial marking M0 is live if no matter what marking has been reached from M0. That means wherever M1 into those are defining different states of your tokens, right? So whatever states, whatever markings you have reached, maybe there is another way to progress, another transition to make. If that is the situation, then your design or your model actually maintaining the property of liveness. Okay. But why this is important? This is important to check whether there is a possibility of deadlock or not in your design. Deadlock means maybe you are waiting, maybe there are two processes, P1 and P2. Now P1 is sending some input to P2 and P2 is sending some input to P1. If in some scenario it happens that P1 is waiting, maybe there are some intermediate processes, maybe direct processing, whatever it may be. But if there is some scenario that P1 is waiting for any input from P1 and P1 is also waiting for some input from P2. So in that case, none of the processes can actually complete their actual execution, right? So in that case, that situation, that scenario, you can consider as deadlock. So this reachability, boundedness, and liveness, these behaviors, these properties we should analyze to check whether my modeling, this Petfinet based, this modeling, whatever we have done so far, whether it is deadlock free or not. So we can take another example and we will see in this way. Take this example. In this case, okay. In this case, these are the transitions. You can check step by step. You will get these are your markings, and that is M01, M1, M2, M3. These are, what I can say, they are actually forming your reachability matrix. Now, so in first case, what is the situation? That you are having your token in P1, that means here, and you are having your token in P4, right? Then you are making one transition. Making one transition is now your token is coming to this token, is coming to here P2, and your this token from P4, there is no transition and it is there in the P4. That means possibly you have done this T1, you have considered this T1 event. Based on this, these transition has taken place and your this token has moved from P1 to P2, right? So that is your M1 state, right? Now from M1 to M2, this transition, what will happen? How it is possible? 0, 0, 1, 0. What does it mean? 0, 0 means there is nothing, no token in this P1 and P2. and not also in P4. That means P2 and P4, both the tokens are now absent and you are only having a token here in P3, right? Now you are moving, that indicates then that when you are considering this event T3, you should have some tokens, or some state transitions from this P2 as well as this P4, right? Then you are having input in P3 and all are rest are 0. P1, P2, P4 all are 0. That means for this T3 event to be performed or to occur, you need to have input from this place P2 and P4. Now this is the situation. You have reached up to 0001. Now, now from M2 to M3, now that means your token is in here P3. From here, you are having one transition T4 and you are again getting back one token in P4. Now you think, from P4, these tokens can only move in this direction, right? That means there should be some T3 event, some T3 event should occur, and based on that, these tokens should move to next P3 or some other place. But here the restriction is to for these T3 event to make it occur, you need to have tokens not only in P2 but also in P4, right? Because based on that, when you have seen this M1 and M2 transition, we have observed that then that time we have seen that this T3 to occur, we need inputs from this P2 as well as this P4. If both are not present, then if this event also there, then maybe you can consider these are the preconditions. If these preconditions are not satisfied, not getting satisfied, then in spite of the fact you are having this T3 event present, this transition will not take place. So after M3, you are only having some precondition in this place P4, but there is nothing in this P2. So one precondition is missing, and that way your situation now is in, you cannot say that your design, your model is following the liveness property. Your situation, your system is dying now. It is not in liveness condition. Okay, so these type of analysis based on Petri-net, it is possible. That's why when we are thinking about concurrency, when we are thinking of synchronous design, the Petri-net is always preferred. So that's why we can say this is a bounded but non-like Petri-net. You cannot proceed after this state. This is another example you can check. Okay, I will go back. So another one is, this is another example of unbounded. That means you are not putting any bound on these tokens. But this is a live Petri-net. Okay. So this is not any type of K-bounded or nothing. So again, you can see here when we are considering these markings, we are considering there are since P, P1, P2, P3, P4, P5, 5 states. So we have 5 column entries. Next, in each state, initially there was P1 all 0. That means your token was here in P1. Then M1, when you are moving, then you are having this P2 and P3. That means your tokens are in P2 and P3 states, and the rest are all 0. So this way, if you proceed, you will see that there is no boundedness mentioned here, but this is a live Petri-net. Why? Because from one state to another state, there is always one transition. So this is these type of analysis. So it is not just we are doing some modeling for the sake of modeling. With our modeling, we are trying to do this type of analysis so that that can be manifested, I mean, with this modeling inputs, whatever, if we feel that, okay, there can be some possibility of deadlock, then we can always modify our requirements, always modify our modeling. Everything we can modify and we can rethink before going to the design. Because whenever we are going to design part, any change will be costly, will be hectic to change. There will waste of lots of efforts before. So that's why we are doing this type of analysis in our modeling part, and then we are proceeding to our design part. So this is the basic idea of PETVNet, this basic importance of PETVNet. So there are different types of PETVNets. You can go through it. That the high level PETVNets where you can tokens of colors, and there are different identities. This is some type of predicate PETVNet, whatever we have just discussed, where we talked about that when we are talking about condition nets, we are just considering just one token at a place. When we are moving to place nets, we are considering that the capacity of each place, how much maximum capacity. So there we are actually considering the boundedness. And when we are moving to this this type of high level PETVNets, there we are considering this predicate nets. There we are considering typical identities associated with your token. Your tokens is not very similar. Whatever tokens you are using, it is not all similar. So also timed features, time delays, those things have been added. And object-oriented concept. This is one example of object-oriented concept. I'm sorry for this sound. This is very disturbing, I think. Object-oriented concept means whenever you are considering this producer and consumer, you are basically thinking them as an object instances of some classes, and you are defining the added features and added functionalities to them. So these features, added features, were added in the later, modified, improved versions of PETVNet. It was not there when it was first proposed, but now with these modifications and with added features, PETVNet is very much useful when we are talking about embedded system modeling. Okay, so these are the few references you can go through. So this is about PETVNet. So is there any question? Hello?
No, ma'am.
No? Everything clear? Okay. Then I will have lots of questions next Friday. Okay. So next, quickly, I will go through a few more maybe I can say, few typical types of modeling. One is a message sequence chart. Now, since we have discussed so many types, I think these parts will be not very complex for you. So message sequence chart means you are considering, you can see with this diagram. Where we are considering different methods, you can see. And we are considering exchanges of methods between these, exchanges of messages between these methods or between these processes. Like here you can see the process A, process B, and so on. When you are modeling all your specification, you are basically dividing them into different process parts, and you are considering what are the message exchanges that are taking place typically within them. Okay. So this is, and there are different, I will come into this part. Before that, there are different symbols present. Wait, there are different symbols present when the message can be lost. Then there are different symbols. Messages can be found. These different symbols. You can add conditions to whenever you are allowing this message passing or actually adding this message passing in your sequence chart. You can add timer. All these features are present. Now, the first question we have to understand is why we are thinking out. We talked about so many good things about PETVNet. We have talked so many good things about FSM, okay, no, let's say for FSM there is a problem that we cannot think about some distributed scenario. But we have talked about so many good things about Petfinet and these things. Still, why we are considering message sequence chart? If you see, as I told that in initial versions of Petfinet, this time delay handling, scheduling handling was not actually considered. These type of features were not considered in Petfinet. So that's why this message sequence chart is particularly useful when you will be considering scheduling between different tasks. Okay. So you can think in this way, you can think this different components in, your time axis, and you can schedule what will be the possible exchanges between your components. So, but there are a few confusions when this message sequence chart first came, that it does not matter which is higher or which is lower in the diagram. That means it doesn't give you the support to understand the precedence. So this is a very basic idea about message sequence chart. Just to give you idea, there are some other types of scheduling techniques are there, and this is typically useful when you are doing your schedule, time-based schedule. Now, whatever we have discussed so far, we have seen different features in their different parts. Like in FSM, we have seen we are basically trying to handling our event-based scenario in a smart way. When we have talked about data flow model, we have seen that we can, when we are just dealing with our system or our model just deals with some specifications, when we will consider input streams and output streams. In that case, we can go to some simpler version of modeling to the data flow model. Then we came to this Petfinet part, where we have seen how we can actually do some better analysis. And also we can consider the synchronization and concurrency in a smarter way. So all these things were there in different tools, and different modeling strategies. And each of them, in this message sequence chart, we have seen, if we consider the different methods and some message exchanges between them, then we can understand what will be my scheduling strategy. That means if I consider two different methods and how they are exchanging the messages, we will understand that when we have to, if we think about in time scale, which message we should schedule first, which message we will schedule later, and so on. So all these advantages were coming from different modeling strategies. Now UML is something, it was, again I'm telling, when if you see there is initial versions of UML, everything was not there. But later on, UML extended, after UML extensions in UML version 2.0 and later, what they have included different components or different diagrams, we can say. Different parts of UML give you different advantages. One is the sequence diagram. Here, this is the same advantage. This is quite similar to your message sequence chart. So in that message sequence chart, what we have seen, we are defining different axes, different components, and we are trying to understand what can be the possible message exchanges between them. Similarly, you can go, there are different state machine diagrams, you have activity diagrams. Activity diagrams are extended Petfinets. State machine diagrams, or whatever we have discussed in state charts. There are some deployment diagrams that includes the related to some your actual execution architecture. Package diagrams, that is basically when you are you are actually developing different software models and you are actually packaging them inside different packages. So how they will interact, those are based on were given by this package diagrams. Then use case diagram, in typical scenario, how you can capture those typical scenarios. and also the class diagram that is mainly related to this object-oriented concept. So including this type of different diagrams, basically UML, you can think under one umbrella, they are giving support of advantages of different tools, different modeling techniques previously discussed. Okay, so why it is advantageous to start thinking first with UML, because when you are actually designing, initially you are having the specification, or you are having some rough sketch of your model, of your specification in your mind. At that time, you never know in which way to go. You do not have practical, in-depth design concepts. At that time, if you will get support from different types of diagrams in UML. And that way, these diagrams can give you, in a layered way, can give you the overall specification to enhance your overall specification, to enhance your overall modeling and design. So that's why UML, with this extension, I'm not talking about UML initial versions, with these new extensions, it is very, it is very effective when we are thinking about embedded modeling. One thing I want to show, I will upload these slides in your Drive folder. This is, I'm not going to discuss in the class, but if you are interested, you can go through this slide. Of course, it is important to understand the UML modeling and UML versions, what are there. So these are the different models and views of UML that is given. Okay. And what we mean by what are the differences between different, like class diagram, like we have just told, activity diagram. Maybe you have now, what I expect that you have separate concepts, but how they are marked in UML, and what are the data types, classes that those are getting supported in UML. This discussion is there. Okay. So this is a very detailed discussion given in this slide. You can go through it, but I'm not going to discuss this in the class, because these are at this point, whatever we have discussed, based on that, this is very trivial. And if you do a self-study, you can understand. Okay, you can see there's use these diagrams, how from one specification you can actually form one use case, or your use case, sorry, not a use case, for how you can actually develop your use case diagrams. So everything is given here nicely. So I will share this with your, in your class slide, your Google Drive. There you can go through it. Okay. Is there any question till now? Hello.
No, ma'am.
Okay. So this is whatever we have discussed. This is almost we have covered our modeling discussion only. From next day onwards, we'll start our design discussion. And for that, another one small topic I will mention about this process networks or task graphs. Maybe we have already discussed it in our previous classes, but just to bring it here. So this is the process network or task graph. So you can see this is one dependence graph where T1, this is different tasks when you are actually trying to model scenarios with different tasks and how they are communicating. So these are the T1 to T2, T2 to T5. We can see these are the dependencies. What does it mean? This T1 to T2, T2 is dependent on inputs from T1. Similarly, T5 is dependent on the inputs from T2 to T5. T2 and T4. So this way, our dependence graph is a directed graph, you can see. Of course, you have to consider the partial order because it is a directed graph, and you have to consider the input from your precedent node. And so based on that, you can, this is quite, I think, intuitive. You can understand what is your immediate predecessor. If V1, V2 belongs to E, then V1 is called the immediate predecessor, and what is your immediate successor. And so in this graph, you can understand for one node or one task, if you draw this type of dependence graph and if you do your modeling in this way, you can understand how, I mean, for one task, what will be your dependency from, what will be your dependency in terms of previous inputs, and if some extensions, if you consider, then from where your outputs are going. Like for T2, this output is going to this T5. So with this task graph, we have some extensions. If we are going to model with these task graphs, that one is this timing information, where we are including different types of arrival time, deadlines, periods, everything associated with your nodes. Basically, these are the extensions. Here you have just considered these nodes. With these nodes, you are associating this on arrival time of the task, deadlines of the task, everything. This is also giving you some idea from where your initial inputs are coming, or which states you will consider as your initial inputs. Third one, you can know what will be your periodic schedules based on your task, based on a task given in the graph. What can be your periodic task? Or sometimes it gives you the idea of hierarchy. So this is, whatever we have discussed before, this is very straightforward from them. Just whatever we have in the dependency graph, from there, we are adding some extensions in terms of timing information, in terms of periodicity, in terms of hierarchy, and we are obtaining this task graph. And there also sequence data flow is possible. Maybe some part we have already discussed in your data flow discussion, where we are considering this synchronous inputs and then some operation so that we can move to the next node. So this is another typical modeling, but these are very limited because you just cannot think only based on task graph. But in these task graph, on your top level, it is important to understand how your different tasks or methods will be communicated, and they can do, and how they will be sharing their variables or communicating in terms of their shared variables. Maybe that in synchronous way, that means synchronous means blocking. You are actually, in this case, this is when you are considering synchronous data flow. I think you know this, that means blocking. If two of these inputs both are coming, if they are not coming till then, if there is some event also, this transition will be blocked. In case of your asynchronous data flow, what happens? This process may be generating some output that they want to give to this B, or some information, some shared variable it is updating, and it is putting in some FIFO queue that we have already discussed in our SDL discussion. There are some additional added storage, added FIFO queue, where we are storing that additional shared variables, and from there next transition is taking place. When B is checking its FIFO queue, it is accepting the value from there and it is proceeding. So there is no concept of blocking. So that way, this is the difference between synchronous data flow and asynchronous data flow. In case of asynchronous data flow or asynchronous message passing, your tokens can be buffered. So these are few concepts, starting from your specification, how you will model your states, how you will model your state transitions, how you can check your scheduling, how you can check your concurrency, how you can check your synchronization. And then when you have done everything, you have multiple tasks, how you can actually proceed and check, a model, how they're communicating on properly or not, and what are the modeling strategies you can define. So all these things we have discussed. Maybe next day, let me know if you have any questions, because I think if you have any questions, you can tell me, or maybe next day you can go through it and just ask me. Okay. So that's all for today. Do you want to ask any question? I think you were having next classes. It's already time is over. Hello?
Ma'am, not about this class. I have a doubt regarding the assignment. Lab
Which one?
assignment. Regarding the lab assignment.
Lab assignment. What is the doubt?
Yeah, I mean, should we embed the C code in the MATLAB or should we give the C code separately?
Okay, maybe what you do, this is not the class for lab. So you can do wherever you feel comfortable, you can do in embedded C platform, or you can do in any GNU platform also. If you are using any Ubuntu system, any C code will be good for this
Okay,
first
ma'am.
assignment. Okay.
Okay.
Okay. So if you have any doubts, I can tell you, do not sit idle and do not wait for the next class. In between also, you can send us a mail. You have our mail ID. Me and Professor Shakil's mail ID. You have TA's mail ID, right?
Yes, ma'am.
Are you having their mail ID?
May not mail ID, but we
Yeah,
know.
I have sent a group mail. So there you can get their mail ID. Okay. Okay. So whatever doubt you have, just send a mail in between the weeks also and get it clear and try to complete and submit the assignments within time.
Yes, ma'am.
Okay, because today is already Thursday, so today is the deadline. So if you are going to solve your doubt today, then of course, you have to do it, submit it. It will take time, right? But
Yeah.
no need to sit idle. Just clear it in between the week and solve it.
Okay.
Okay, so that's all for today. Thank you.
Thank you, ma'am.
Thank you, ma'am.